And I'm Dilini Abeygunawardane, and this is Philippe Rufin. And we also wanted to mention Christina Chiarella. So she was actually the mastermind of this session. Unfortunately, she couldn't make it here. So if you want to contact her by any chance, her email is up there. So Philippe, do you want to take over and say a few things about the session?
Thank you. So we discussed, the three of us, the three session organizers, this topic for quite a while actually, because we realized there are many processes going on in the global south and agricultural land systems that are really essential for sustainability questions, really essential things for the SDGs. So we think about changes in the structure of the agricultural systems in the global south. It can be changes in field size and farm size. It can be changes in land management that manifest in some way, crop diversification. It can also be changes in labor and employment opportunities. It can also be changes in migration. So many of these things we don't really observe from above. We're not able to observe them with our eye, but we have to go and speak to people, and that's where micro-census data comes into play. So household surveys and census data is really rich with regards to the properties we can record, but we usually don't access it at scale, but we have it at the administrative unit level, at the national level, so it's not really fit for purpose if we want to dive into spatial patterns in more detail. So recently there are quite large advancements in data collection efforts, so you may be aware of the LSMS survey waves that are being collected in more denser intervals, so we get more temporal depth, we have nice panel information for many, many countries, and they are also being complemented more and more with geospatial information, for example, the location of the household, or in some cases even the location of crop fields. And this is really a great data source, but still we cannot really scale it up, and this is where Earth observation comes into play, because we may be able, if we find the right ways, to kind of extrapolate in space these properties that we have measured at the household across larger landscapes, entire countries. And this is more of a vision than anything that is already put into practice. Christina was the bright mind to suggest we propose this session here, because we believe there are many people that are occupied with this topic, interested with this topic, and also to find and scope a bit who is actually already working on that. So I'm happy to present today 4 speakers that we have that will in parts present advancements in Earth observation that somehow lead us towards indicators that we can produce at scale that may be able to allow us to link with micro-census data, but also a few ideas and suggestions on how to actually do that job of linking Earth observation and census data. And with that, I'm happy to invite the first speaker. It's Urs Schulthess from CIMMYT, who is presenting today on behalf of Katharina Waha, who unfortunately could not make it to the session today. So if we switch the slides.
Thank you, Philippe. Okay. ¿Se puede bajar la luz? Okay. Well, I'm starting. So, yeah, we have different offers. So I collaborated actually on a paper together with Katharina, and we have collected data from different places around the globe, and that's why I'm sort of part of this presentation. Okay, so why do we focus on smallholder farmers and field size? Well, smallholder farmers are very important because usually they have high productivity, but they're also affected by poverty, and it's also a very dynamic system because farm sizes change. In the past, it used to be like a farm would get divided up usually among the sons, but there is also nowadays more and more migration out of the farming system, because farming is often related, especially smallholder farming, very often equals poverty as well. But smallholder farmers also play an important role because they also they're sort of aware of all the traditional systems, like here in Mexico we have these milpa systems where farmers actually intercrop maize with squash and beans. Oaxaca is a very important region for that, for instance. Okay, here's just the illustration. And so there's a few challenges because on surveys often they are not really, well, people in general, I guess, they not always tell the truth in a survey. Sort of they think like, what's in it for me? But also farmers often don't know the exact size of the fields, which is also a problem if one like generates recommendations. And it's also surveys, especially household surveys, they're very expensive because one has to go visit every farmer and also take up the time of the farmer and so on. And in remote sensing, we have now new opportunities. We have like half meter data or 0.3 meter data. Like half meter data, they're available like for 25 square kilometers at the price of about $300. So it's sort of affordable, opens new opportunity. But then also with remote sensing, we can then also like analyze landscape and habitat fragmentation. I come back to that at the end of the speech. And there's also like a lot of data which actually could be exploited more. For instance, the World Bank supports like these integrated household surveys that are taking place, for instance, in Malawi every 5 years. And one can complement those survey data with remote sensing data. And what I mentioned before, we now have these high resolution satellite images, and they can be used to basically create field boundaries. So then we can like map sizes of fields, and it also helps for crop identification and other information. Sorry. Okay, so yeah, these are like quite a few papers have come out in recent years. And also we have, obviously, it's not only better images, we also have better algorithms, especially these neural networks or convolutional neural networks, CNN. They're very powerful, although they also need good data for training. And there, like here on the left side, there are quite a few examples of commercial use of field boundaries, but usually they are more for larger fields. But also there have been global efforts basically to map the distribution of field size using crowdsourcing and other tools. And so basically this shows like what we can learn. So this is data from Katarina, like shows that the field size usually also related to farm size, so larger fields belong to farmers who have larger holdings. But there's like this field size information is part of like various components like labor use, poverty, machinery, and so on. And then also obviously sustainability, which is important. And so how would that work basically? So how can we combine field boundary information with remote sensing and survey data? So this is also, actually, this is, if you have like information on field and farm size map, these are some data from different countries in Africa. So we have like countries like with, where the fields are very far away from the farm, like in Niger. Ethiopia, for instance, has a lot, farms tend to have many, many fields. And in Malawi, for instance, fields tend to be close to the homestead. And this is a size, like a map of Malawi. Basically, on the y-axis is north-south, then east-west. So we see, like in southern Malawi, farms tend to be smaller field sizes. It's also more dense. In the north of Malawi, we have the larger farms. So that then also allows like people who do the surveys, like household surveys, you can actually then figure out where to go so that you get a representative sample, so that you get farmers with large fields and also the ones with small fields. And as we had seen before, like small fields are usually related to small farm sizes. So this is now sort of a model for next generation monitoring of agricultural land use. So we have like first we need to create like a field size map or create field boundaries. And then next we can link those to survey-based geospatial socioeconomic data. And that allows us then to map like smallholder farms and also their livelihoods, and that then helps us better understand processes of land shrinking, farm expansion, also fragmentation, consolidation and persistence. Since, as I had mentioned before, it's a very dynamic system. And so this is now basically a table that shows how the satellite data and the survey data can complement each other. There's actually also one more column one could add, that's basically household surveys. So it's not these national agricultural surveys, they're usually large databases that often are accessible, but then one can also conduct one's own household surveys to find out more about why or why not farmers accept the new technologies and what opportunities there are actually to improve the livelihood of farmers and so on. So we have different indicators, like starting with field size. So as I mentioned before, we can do field boundary detection, farm size next, and then information we can only get from surveys like use of family labor. And then what's also very important, because usually we assume they have small farms and a lot of family members, so they have plenty of time, but it's actually not true. As even smallholder farmers are very often very time constrained, because it's also, like for instance in Malawi, a lot of the land preparation is done by hand. So therefore, it's important also to see like where are opportunities to make better and more use of machinery. Then we have we can then indicate another indicator is like on sustainability of land management. We can then also look at like how much inputs they're used, and also actually assess productivity, because then with remote sensing we can pretty much or quite accurately, at least for like cereal crops, we can estimate productivity as well, and also production systems. I mentioned before, like in Mexico, where there's a lot of intercropping, or also in Malawi, where we have seen that like farmers that have smaller land holdings, they tend to intercrop more than the ones who have large land holdings. Those with large land holdings, they monocrop, because it's you can mechanize it better and requires less manual labor. And then obviously at the bottom, that's the very important indicators are like related to farm income. And so that's, you don't see that with remote sensing, but you can get that from the survey data, poverty mapping, and then also like you can learn about farming activities, and also figure out where it makes sense to target some technologies. And that's sort of, I'm coming close to the end of the of my presentation. And actually this is from, I think it's near Würzburg, where Katarina works. And here you actually see quite nice differences. You see an area with like large fields, small villages, and then we have an area over here with small fields. And also I assume that this area over here may have been flooded before, and then all the villages are like on, farmers live on either left or right side of the depression or of the valley. And then also up here you have like integration with forests and so on. So if just by looking at the high resolution satellite image, you can already learn quite a bit and then also determine where do you want to go for a survey. Yeah, thank you. I don't know, it's questions now or at the end? Oh, sorry?
So we take a round of questions. Sorry, I was looking for a second microphone, but we only have one. There's one. Ah. Perfect. Okay. Does anybody wants to ask a question to Urs regarding what was presented? Nobody yet? I don't think it was confusing, but you provide a lot of answers to the session topic that we put up there, so I think it was a nice talk. Okay, if there are no questions from the audience for the moment, we continue with Zia. Okay, Zia is from the Better Planet Labs, right? Okay.
Brilliant. Can you all hear me okay? Cool, we got the lights. My name's, as this is coming up, my name's Zia Marabi. I work at the Better Planet Laboratory. That's at the University of Colorado Boulder. And I'm going to talk to you today about deep learning waterways for rural infrastructure development. We're breaking the rules a little bit for the session. I couldn't really find a good session for this talk, and the organisers very kindly let me co-opt their session to communicate this research to you. If you want to find out more about our lab, it's thebetterplanetlab.com. I'm presenting this on behalf of a machine learning engineer and myself. We worked on this together. He worked at the lab for a couple of years. His name's Matthew Pearson, brilliant engineer. Let's see if I can get this to work. Perfect. So this is the kind of output that I'm going to talk to you today. And the first thing I want you to recognize from this kind of output is it's very beautiful. What you're looking at here are waterways that are mapped at a resolution that have never been mapped before in a particular area of Rwanda. But the second thing I want you to take home from this is that this is not just beautiful, it's very important. And the reason why it's important is because there are a number of communities in Rwanda and elsewhere around the world that get cut off from essential resources. These are children who can't access schools, pregnant women who can't access healthcare facilities, and farmers that can't access markets, right? If you take away rural infrastructure, and in many cases the rural infrastructure doesn't exist, these individuals don't have the human right to access these services, essential services. And so over the last few years, we've been working, if it's going to advance, yeah, cool. We've been working with a NGO called Bridges to Prosperity. They're an NGO that builds rural trail bridges. And we've been using logistics models to try and work out the impact of these kind of bridges on reducing the travel time that it takes for children to get to school throughout the year, you know? So it's not that they'll be cut off necessarily every day of the year, but due to flash floods and things like that, they could be cut off for a number of days of the year. And mothers won't send their children, mothers won't send their, typically, girls to school because they don't want to be caught on the other side and not make their way home. And so Bridges to Prosperity has been leading the charge on building rural trail bridges in these particular locations. Now, one of the challenges that they have is they can't remotely assess the impact of these bridges. They want to do national-wide programs, and they're very ambitious in their scope because they believe that these rights should be realized. And so we developed these logistics models to try and work this out for them. And we released this product called FecaMap alongside Bridges to Prosperity. This is an example. You can go to our website and check it out. But fundamentally, it's a tool that Bridges to Prosperity using internally and with governments to identify the catchments, the populations that are served by having these rural trail bridges. Now, what we found out pretty early was that many of the requests that communities were making for rural trail bridges fell on places in the map where there were no water. And we looked, and we'll get into this throughout this talk, we looked at the best data sets that are out there, and we were dumbfounded because our logistic models we're also concerned, right? Our logistic models depended on us having accurate representations of the obstacles that people needed to face to get to where they're going. And so this led us down the path. It wasn't our plan. This led us down the path of mapping waterways at very high resolution. It was never our prerogative to do this, but we had to do it to get where we wanted to go. And so what we ended up doing is training a computer vision model. It's an adaptation of UNet, if any of you know about UNet and ResNet, these computer vision models. It's trained using high resolution vector data from geographies like in the United States that have very, very high fidelity data. We combine that with satellite data, namely Sentinel-2, and we're typically using the RGB, so that's like your kind of typical thing you'd see in a photo on your phone, alongside the near infrared, and a digital elevation model. And we basically train these models to draw waterways, right? And these are the kind of outputs we have from this. And just to give you some perspective, this is the coverage, so you can get a benchmark. The last set of plots on here are the USA, and this kind of gold standard, one of the best waterways data sets that exists in the USA. This is the NHD data. And this is the percentage of our waterways that are mapped, that line up with NHD. And what you can see is, NHD is doing pretty well, right? Like if you live in the USA and you want to know where water is, you want to know where to build a bridge, you have pretty good waterways data. Like we know a lot about the USA. I want you to look to the left of the plot here at Africa. And the most commonly used data by NGOs and other organizations is in pink, it's OSM. And what you can see is OSM, less than 20%, often 10% of waterways are actually mapped across the continent. There's other data sets like this TDX Hydro, which is less accessible to a number of organizations. It gets better coverage in some of the classes. So these 0-3 is higher class waterways there. This is a visual representation of what we're doing. These are 3 locations in Ethiopia, Rwanda, and the Ivory Coast, 3 locations that we work in. And what you can see on the left-hand side is these maps, these raster data sets, and we vectorize these data sets. Everything in orange is the best-in-class data that's developed by the National Geospatial Intelligence Agency, right? Many scientists working on developing this kind of data. And everything in blue is what we've added to that. And what we're finding is very, very striking. What you can see here in orange is the baseline that these organizations are currently using, OSM, and it shows you the percentage of community requests. These are requests that communities are making for bridges, and you can see the coverage. In some locations like Rwanda, you get pretty good coverage, like 70% of those bridges are being mapped on waterways. You go to somewhere like Côte d'Ivoire, and you have around 10%, less than 10% of the requests that communities are making are actually falling on waterways. With TDX Hydro, you can see that's built with a 12-meter DEM, best in class. You can see it's good in some locations, but in others, again, like Côte d'Ivoire, in Liberia, you're still less than 50% of community needs are being represented. And at the top, you can see our new data set. We're capturing 95% of the needs across all of these different geographies. So this has been pretty fundamental, for Bridges to Prosperity. They're now using this waterways data set, which we've fed back into FICA-MAP, and putting this in front of governments, particularly in the government of Zambia and some of the other countries that I've shown you, to initiate programs for site assessments for building new bridges. So we've seen a very rapid, over the period of 12 months since when we started this project, delivering this technology to BTP, them implementing it in conversations with governments, with funders that are leading to these bridges being built. And so it's a really beautiful kind of example of, how remote sensing and, and this kind of technology can be used. This is kind of like eyes from the sky, but with data from boots on the ground, to realize human rights and realize positive outcomes for people. Now, as I said, it's important, but it's also beautiful. This is an example from northern Rwanda, and what you can see in the north part of this image is the rendering of the ways that water will flow over volcanoes. And as you can see, they look like flowers, right? It's absolutely beautiful. And so this data is also really captivating And we see a lot of avenues for using it for art too. What we've done over the last little bit is to take this model and deploy it everywhere in the world. So we have the world waterways mapped in rasters at 20 meters resolution, and we've vectorized that data, and we use TDX as a backbone so people can put it into their pipelines. We tripled the extent of waterways mapped globally with this product. And we see many kind of, applications for rural infrastructure, but also other things too, like Earth system science. And we're looking to drop the preprints next week. If you're interested, stay tuned for it. And yeah, thanks so much.
Thanks so much, Zia. Very inspiring talk, I think. Nice showcasing the potential of deep learning, Earth observation, new technologies that you leverage there for new products. I'm sure there are questions in the audience.
It's always nice to talk, very nice talks, dynamic. Of course, it's very high tech, for us. My question maybe is on the training, how much, I know you're not very fancy machine learning or this thing, but you need data, right? If it's just very remote area, I don't know what kind of how much ground truth or training data you need to actually get the beautiful map as you show. And then another related question, I guess, the validation, it's not everybody can have a map, right? How reliable? Obviously, you should be very reliable because they build the bridge, right? Using your data, you have to. I hope you don't build the bridge to nowhere,
Yeah.
So maybe more on the first question, for us working for this remote area is always very expensive for you and me to go there to get the data, to train your model.
Thanks so much for the question. So validation is difficult, right? With a product like this, where something's never been mapped before, you have no intercomparison. Right, and often even in like cropland products that we develop, right, we're intercomparing them. We don't necessarily even have, on the ground data. In this case, there's a few things that are encouraging for us. The first thing is that the NHD data, we know there's some missing waterways in there. We're capturing more. There's more than 80% agreement. So we're not drawing. If you think about the global picture, where I said we've tripled the number of waterways mapped globally. If you look at areas where we've mapped really well waterways, there's an agreement of 80%. So there's factors of difference in terms of what we're mapping at, the gaps that we're filling, and when we actually have the data to validate with. The model is trained on over a million basins, like chips from basins. Sorry. And it's trained predominantly in the USA. Originally, we were concerned about this because we didn't necessarily have the intercomparisons elsewhere. But the intercomparisons that we've done in Europe and in the USA, where we have those intercomparisons, suggest that we have good recall, but we're not necessarily losing precision in the process, right? The problem is false positives, right? And so that kind of gave us that indication. But there are many locations in the world where waterways aren't mapped very well that will need further validation. For our case, and for this particular project, one of the unique things that we did have was these bridge requests. And those bridge requests, as you say, they're not coming from locations where there aren't waterways. One of the things that we have done is that we've looked at places where we have good waterways data. We've looked at the whether we are likely predicting ephemeral and intermittent waterways. And obviously we're predicting a lot more first, second order streams too. We think that we are capturing intermittent and ephemeral waterways that have been left off maps to date. And that is fundamentally critical for a lot of these communities. It aligns with what we're hearing on the ground, that it doesn't need to be running all of the time. And if it's running for 10 days of the year, that can be an obstruction. And so we're picking up those waterways too. But there's a lot more validation to be done in other areas, yeah.
Okay, we have one more question from the audience.
Thank you for the fantastic talk. You mapped the waterways, right, for building that bridges, right? Maybe I do not get the full picture. I think maybe you also need to map the road. Otherwise, you build the bridges goes to nowhere, right?
So, thank you. Yeah. So, prior to mapping waterways, we developed logistics models to work out the time it would take for someone to travel from their village to a destination. That could be school. We map schools, healthcare facilities, and urban centers for population centers for markets. Now, when we build those models based on road data, pathing data, elevation data, data on how long it takes for someone to travel over different types of terrain, over different elevation gradients, different obstructions. The existing bridges are in there too. So there's a whole load of geospatial data that's involved in FICA that includes all of that too. And so one of the fundamental missing pieces there is waterways, but there are some locations, for example, in Ethiopia, where even the road data sets that exist, and even the ones that are developed by Microsoft, they miss many roads. One of the interesting things that we found, and I'm presenting it here today, we can take this model, the segmentation model, and we can train it on road data, and it can fill in those gaps. We found it to fill in the road gaps in Ethiopia too. It's pretty exciting. But yeah, you need to know all of that stuff too if you want to actually work out where to place a bridge. Yeah.
All right, excellent. We had good questions, good discussions. Maybe a brief question from my end to you. Are you going to make the data available to us?
So the preprints and the data are likely to be made completely public next week. So there's two preprints that go with this work. All of the vector data, all of the raster data, which will be in their chip downloads. So like they're, be a couple of gigabytes each. But overall, you're talking like very large data size. We're also working with Source Co-op to deliver it on an API. So for programmers that want to use this in their pipelines, that should come in the next few weeks, if not a month from now.
Excellent.
Yep.
Round of applause for Zia. Thanks for making the data available as well. Nice. Next up, we have Dilini.
So, hello everyone again. I'm Dilini Abeygunawardane. I'm a postdoc at EAMO. So it's a Leibniz Institute, the one for agricultural development in transition economies in Germany. And what I will present to you today is an impact evaluation we did in Mali that was commissioned by SPIA, the Standing Panel for Impact Assessment of the CGIAR. So SIA had a very positive story, but I guess I'm afraid we don't really have a very positive story, but how you interpret it might also depend, and we'll get to look into that. So just wanted to give a big shout out to the team. We have a wonderful team from all over the world working on this, many experts from different fields, econometrics, remote sensing. Some of them you already see in the room. I saw Robert in the room a while ago, but I don't think he's here anymore. There's Daniel, there's Philippe, and then there was Patrick, and a lot of many other people who just helped us make this happen. And also a team on the ground in Mali doing the ground truthing work and a lot of validation work. So a big shout out to them. And then, it's that way. So what is this project that was commissioned by SPIA? So it was this ICRISAT's large-scale agricultural intensification project. Basically, the region that we focused on is Sikasso, because Mali is a region where you do have a lot of militia activity, so we focused only on the south. But even in that region, the program reached out to more than 100,000 sorghum and millet farmers, and they received this technology bundle to improve their yields. So, what happened is a success story. They improved their yields. Millet yields improved by 30%, sorghum yields improved by 60%, and there was an economic rate of return reported of the range of 24%, and they also reported that the household incomes have increased by 133%. So this was a cost-benefit analysis done by the USAID following the project. And so what the assignment we had was, if this is what happened, what would be the environmental impacts of these intensification efforts? So normally these are not targeted towards large-scale agricultural farmers. These are subsistence farmers. But even in the case of subsistence farmers, are there negative environmental impacts that was intended for some good in the first place? So our hypothesis was, if there was these yield improvements, then did it actually cause heterogeneous impacts on the land use and land cover change? And to understand this, we know that most of us have heard about Borlaug and Jevon's arguments, right? So if there's yield improvements, this should either yield to land saving, or it could also mean that there would be labor and capital reallocation leading to more production. And in that case, are we going to expand production? And this might, there's a lot of work done on this. So Robert is back. So this might, based on the market conditions and how connected these markets are and the demand elasticities of these crops. And one thing that I wanted to highlight here is something that Ben Phelan reminded us recently at a conference that we had. He reminded us that land saving is not land sparing. So oftentimes, even I used to say, like, it's land sparing versus the rebound effect, but what we're actually measuring here is land saving. In the case of land sparing, what Ben Phelan, who was actually sort of promoting the land sparing model, he was among the pioneers of who brought up this idea. What he was saying is land sparing is a biodiversity conservation model, but what we are measuring here is actually land saving. So as I told, like, this story, like, depending on what the outcome is, like, it depends on how we interpret this. So we can come back to this later. So I think I went back. Yes, so based on that, we asked simple 2 research questions. So what's the impact of Apologies, ARDTSMS is the intervention package. So what's the impact of this intervention? And we used 2 metrics, woody cover and cropland extent. And then how did this vary across market conditions? And in this, we used cotton area as a proxy. Okay, I keep going back. So before we move on to understand how we did this, let's just briefly look at what we found. What we actually found was a rebound effect. So in the case, like, we found a decline in the woody cover, a 0.9 percentage point of decline, and then a cropland expansion of 3%. So these are the causal effects that we estimated. And then let's go on to see, like, how we achieved this. I think I'll just, okay. So apart from the fact that this is where the money was, like, why is this project important for us as well as, like, for the larger community? So in this Sahelian region, tree cover is basically, outside of conservation regions, you see that the largest percentage of tree cover occurs in farmland. And if you also compare the woody cover or the tree cover between in the semi-arid regions between farmland and savanna, you do notice that in the farmlands, actually the mean is very close to what's available in the savanna. So this is why we think that the matrix we use to assess the impact of this intensification project is quite important. So, and doing this, we obviously know that there are always challenges. So because development projects, they don't plan these development projects and deliver them in a way to sort of gain the least possible benefit. They always target it in a way so that they get the most benefits. So villages were selected in a way that there were project partners. This is where the best agricultural potential was, best market access and site accessibility. And also, so like in the rainy season, they really considered whether they could go access these villages because some of these parts do get inundated. And their beneficiary selection, most of the beneficiaries were self-selected into the program. And one other thing we need to focus here is that the timing of the intervention, it wasn't spread over a long time, although the whole project was spread over like from 2014 to 2020 actually. The main intervention, the main technology bundle was delivered during the 2 years. So we just considered this as single point of intervention. So, with those endogenetic concerns, we also need to look at what was happening on the ground. So, like if we look at the treated villages, where they received the interventions, and the other villages, you see that there is not so much difference if you look at the area cultivated, crop sales, and even the crop yields, which I haven't put up here. But having said that, it also depends on the data sets we use. Still, the differences between the treated and the non-treated groups was still slight. We didn't detect any major differences. And this is good for our analysis, right? So we are not seeing too much difference. Still, as I said, this depends on the data sets we use. So we did make measures to adjust for whatever the differences there may be. And one other thing is, like, if you look at the woody cover before treatment between the treated and the untreated villages, you see that the untreated villages already had a higher tree cover, and the non-treated treated villages had a lesser tree cover. So our identification strategy had to account for all of these things. The selection bias, as well as the other differences that was between treated and the untreated villages. So we came up with this model, which is the outcome variable, which is woody cover, or the other metric, cropland extent. In either case, this depends on, of course, the intervention, but you see that the intervention is simultaneously affected by other factors and also the outcome variables. So because of that, in DAG language, we say we have to close the backdoor paths, and we control for geographic, environmental, and climatic factors, as well as other development interventions. But I would also like to put a question mark on other development interventions, and then we come to the question of data. I think, Philippe, I'm going over time a little, right? Okay. So, and apart from controlling for the confounding factors, we also introduced a bunch of covariates, and then we matched for these covariates to make sure that the estimate that we are getting is like unbiased. So, how did we do this? We generated a panel of remote sensing data, and this was a work in itself and a paper in itself, and this took like more than 3 years, so I'm not going to do justice for the remote sensing work we did. But basically, we have tree cover and cropland data before intervention and after intervention. We had multiple reference data, both on the one hand to create the survey designs, and on the other hand as training data. And the modeling to reduce the noise in inter-year variability of the STMs. They used land trend smoothing. I'm not a remote sensing specialist, so I have to switch to the day now. And they ran this in a random forest model, and also used nested cross-validation, both internal and external. And we also had a lot of validation data, both on ground data, ground validation points, 4,600 collected on the ground, across a region of 70,000 square kilometers. So we are talking about a region of around Ireland or Georgia. And also we added 2,500 more collect earth points. So the remote sensing products we got I'm always very grateful to the remote sensing team. Philippe was a part of that. So we got very high accuracy. And this is just a visual interpretation of what we got. And you see the errors are very low. And we did get a very good model fit. And this is kind of the amazing work they did. And just to remind you, for other regions with closed canopy forest, we do have like good data products, but we are not working in that region. So in this Sahel region, they had to sort of like reinvent the wheel in a sense to sort of come up with this product. So coming back to the findings again, what we find is obviously there is a decline in woody cover. This is the average treatment effect. And we see that the cropland declined, woody cover decline within cropland is 0.5%, and outside cropland it's 1.5 percentage points. So what it means is like, and then if you go to the other point, cropland expansion was 3 percentage points. So if you put all of this together, you see that actually due to the intervention, they were expanding outside of cropland, and that's where the woody cover decline happened. And something else is very important. If you just look at the time effect, not the DID, but just the time effect, you see that there has been a gain in a 4 percentage point gain in woody cover outside of cropland. So it kind of sits well with the story that we've been telling. So if the the intervention had not happened, then apparently based on this result, there should have been an increase in woody cover. So we then looked at the conditional effect of the treatment, and we do see that if you look at the graph on the right-hand side specifically, you see that cotton had an effect on this. So like if you're thinking about areas with higher cotton area, the woody cover was less. And if you're talking about areas with much more cotton areas, you see that the woody cover is less. So the treatment did have like heterogeneous impacts. So this is just the summary again, just saying that in Mali, it was a rebound effect, but we need to remember that, as Ben Phelan said, this is not land sparing, this is not, this didn't happen on land saving, this happened. So I think it's a good point for us to think if we try to kind of attach some normative lens to this. With that, I guess I'll end my talk.
Maybe you want to drop another question to one of the earlier speakers, so now would be the chance to do so. Everybody's eager to leave the room. Okay. All right. Then we take it from here. We are closing the session, the last session of the day, before the Grande Fiesta. We are looking forward to exchange more in person outside and have a chat in a more relaxed setting with some fresh air. Thanks very much for joining. It was a well-visited session. Really nice that you all came and stayed with us. So see you soon. Bye-bye.